Okay. Well, I thought it was pretty exciting to be in the Pilbara listening to all the speakers this morning. But it's actually also a really exciting time to be alive. Technology these days has been increasing our wealth, increasing our standard of living, decreasing world hunger, doing all sorts of fantastic things. The change in technology, it's making some goods more affordable because there's lower cost production, but we're also developing new goods to deal with new needs and things that were really never imagined before now. Take the communications revolution as an example, because I know there's a few of you that are tweeting here and so on. But instant communication many years ago was handled by the telegraph. That then moved on to the telephone. Those telephones ended up in everybody's home, and now you've all got these phones in your pockets. The materials of construction had to be changed as these technologies developed. They need to be reliable, they need to be fashionable. So the telegraph was using wood. Those phones started being made out of Bakelite. We then moved to thermoplastics, and now your smartphones are made up of composites of plastics and glass and metal. All of those things have become more affordable as our technologies developed. With these materials, not only are we developing new materials such as plastics, but we're also finding new uses for old materials, and that's kind of where we're fitting in. You know that the Pilbara is a fantastic location for producing solar salt. It's a very dry environment, it's hot, large areas of land that aren't used for any other purpose. But it's been made that way for some 10,000 years, and salt started off being a food supplement and a preservative for foods. But now it's the basis of all the chlorine-based plastics in our lives, so PVC, polyurethanes, and we couldn't actually live without them. So there's an example of new uses for an old material. But the ocean doesn't only contain sodium chloride. It actually contains every naturally occurring chemical element on the planet. Magnesium is the metal that's got the second highest concentration in seawater after sodium. And that's where EcoMag's focusing our efforts. So EcoMag as an organisation was established as a private company in mid-2015, and we moved to an unlisted public company in October 2016. Our purpose is to extract high purity magnesium compounds from brine solutions or salty water. We're currently part of a world-class 300 research program in South Korea in partnership with the Korean Chemical Corporation and the Republic of Korea government. The program's worth $10 million over 5 years, and the goal of that program is to research commercial applications for high purity magnesium compounds. EcoMag's built a small-scale pilot facility at Korea Chemical to develop these compounds, and we're also constructing a mobile pilot plant that we're going to deploy in Australia later this year. Magnesium historically magnesiums come from mining of minerals such as dolomite and magnesite. It's hard rock mining, need to remove the impurities, and then you roast it to convert it into magnesium oxide. The global market's around about 10 million tonne a year from these mined sources. And the traditional uses for these things have been in high temperature applications such as refractories or ceramics, in building products and in fillers. Magnesium oxide is also smelted to produce magnesium metal. You'd probably all be aware that alloys of magnesium with either steel or aluminium are far lighter and far stronger than the steel or the aluminium alone. And it's these benefits that lead to energy efficiencies in all of the technologies that we're dealing with. Nicole mentioned earlier about substitution of products, and it was talking about a real downside for the commodities industry. But substitution has happened all the time, and material scientists therefore are working on new uses for those materials that we've traditionally used, and they're also looking to find new materials that can be used in these new technology applications. And that's about improving the performance, improving the efficiencies. Rick talked about our challenge for batteries, and we talked about lithium-ion batteries, but there's a big gap between where batteries are now and where batteries need to be. Well, magnesium has a much higher energy density than lithium in battery sources, and it's a very promising battery technology. There are heaps of challenges around the electrolytes that are used in the battery to effectively use a magnesium battery, and Toyota last year invited a bunch of people to try and solve that electrolyte problem. So looking forward to how that develops, because that's probably going to move us to that electric vehicle situation we need to be in. So old materials such as magnesium that's been around for a long time as an insulator can also be used for new applications such as these batteries that we're going to. EcoMag's magnesium extraction technology, we've applied it to a bunch of different brines. It can be used on seawater directly, it can be used on salt field wastes, or it can be used on inland salar brines. Around the Pilbara, we're obviously interested in salt fields, because that's where they are on the coast. And we've demonstrated the successful production of a high purity compound out of a variety of these brines, bitten sources from around WA, and also working with Callium Lakes Limited, who are proposing to develop a sulphate of potash operation at their Biondi operation, some 80 k's southeast of Newman. Now, there aren't very many technologies out there for taking magnesium out of brines, and the majority of them involve pretty harsh chemicals, caustic soda and stuff. Our process has got some advantages, that it's using benign chemicals that reduce the hazard exposure that people are exposed to during their use. It also has a lower CO2 footprint than the other technologies. Our technology is patented and licensed out of Chonam University in South Korea. That's why we've been doing our development work there. And that technology actually originated with our technology director, Professor Tam Tran, who is currently working with Chonam University. But he started this technology development when he was here in Australia working for University of New South Wales. So it's an Australian innovation that's gone overseas, been developed to the point it's commercialised, and we're going to bring it back to Australia and demonstrate it commercially. So this is just a bit of a flow sheet of our process. As I said, it can be used for a whole series of different types of brines, and it's complementary to existing operations. When you crystallise or when you evaporate seawater, the first thing that comes out are calcium compounds such as calcite and gypsite. When you further evaporate it, sodium chloride comes out, and that's the basis of the solar salt industry. Further evaporation crystallises mixed salts of potassium and magnesium. That's the basis of the potash industries that are being developed in the state. And then the final brine that comes out of that is a high magnesium solution that's ideal for us to extract magnesium from. Our process can be applied at any stage in this evaporation cycle, but it's most commercially viable after the salt has been precipitated. In our process itself, which is kind of the lower box there, we've got to remove calcium because calcium's an impurity, and that'll adversely affect the purity of the product that we're dealing with, and we are very much in a high purity market. We filter and wash the magnesium precipitate that we produce, and we then dry it using solar greenhouses and some conventional drying. And we'll then roast it at 600 degrees to produce magnesium oxide. We've actually demonstrated the viability of the technology on some lithium brines, so where people are extracting lithium out of salty water solutions, magnesium in those lithium brines actually causes a reduced recovery of lithium. So using our process to remove the magnesium before you take the lithium out has significant recovery benefits in those processes. There's also been a very similar technology that Chonam University has licensed for producing high purity manganese, and that was licensed from the Chonam University into Dongbu Metals, who are South Korea's second largest steel producer. So although we haven't actually demonstrated the process ourselves on a commercial scale, there certainly are related processes in there that are working. Our plant's relatively simple. It consists of a few ponds, it consists of some reaction vessels, and it consists of some filters. We then take our product and we put it into solar greenhouses. These things are used pretty extensively around the world for drying sewage sludge and that sort of stuff. Applying them to a mineral processing sort of operation is pretty innovative and new, but it also reduces the thermal load on the whole process and therefore reduces some CO2 emissions. We will then be roasting the product to produce magnesium oxide. That CO2 that we take off the roaster can be recycled back into our process to produce the precipitation reagents and create our magnesium carbonate material in the first stage of the process. There are a bunch of synergies around Karratha, and Alana mentioned this morning the Sahara Forest Project and Yarra Pilbara Fertilisers. We're partnering with them in a sustainable industry hub at the moment, and along with the city of Karratha. This 10 megawatt solar array with battery storage that we're talking about, we're a significant user of that. But these synergies around these organisations are actually broader than simply utilities like power, water and roads. The process streams from each of these organisations can be relocated between the others. So brines from desalination of water can be used to cool the greenhouses, so can the wash water from the EcoMag process. The high purity water that we collect off the solar dryers can then be used to either feed back into the water systems or into the renewable hydrogen space where Yarra are looking to develop their expertise. That water can also be used for irrigation. So Sahara Forest are about producing vegetables in greenhouses, but also talking about producing crops in the land surrounding the solar array. And that obviously needs water to irrigate it. So combining these groups together actually creates a stronger and more eco-friendly outcome than each of the individual projects on their own. And I think that's a key to the future of the development of sustainable industry. In terms of our products out of EcoMag, the primary product is hydrated magnesium carbonate. This is the high purity direct precipitation product out of the brines. We can remove about 95% of the magnesium out of the brine solution, so we get very high recovery, and it's greater than 99.5% pure. I talked about magnesium compounds from mining. They're typically 80 to 92% pure, so this is definitely a different end of the market. Although it's a similar material, it's certainly working in a higher purity space. The hydrated mag carbonate sells for somewhere between $650 and $1,900 a tonne, but it's really an interim product. Roasting it to produce magnesium oxide is one of the key things, and that magnesium oxide can also be converted to magnesium hydroxide, and I'll talk a little bit more about those in the next slides. So there's a few things that this stuff's used for. The magnesium oxide is actually used in glass. That's where the high purity magnesium space is. So all of you have got your mobile phones. Gorilla Glass is actually glass with magnesium in it. It's got about 4% magnesium in it at the moment, and hopefully now if you drop your phone you're not going to smash the screen. Corning and Saint-Gobain, the US and European glass makers, have taken some samples from EcoMag. They're very impressed with the quality of the material. They've asked for some much larger samples. Unfortunately, we've only had lab scale stuff so far, and those requests for samples from those downstream markets are some of the key reasons why we're developing our pilot processing facilities. They're also looking to increase the magnesium content of glass up to probably closer to 8%. And that'll decrease the weight quite substantially. It'll probably then have potential in skyscraper buildings. When the glass gets lighter, the panels up the top of the building can be much thinner. There's a lot less weight, a lot less foundation required for the construction of the building. Magnesium hydroxide is a flame retardant. Plastics in our home quite hazardous if they catch fire, release toxic fumes, and they can actually get quite serious flames and very hot. Most of the fire retardants at the moment are organohalogen based, probably bromine predominantly. And they use bromine because it doesn't actually decrease the strength of the plastics. But bromine has significant adverse health effects, and it's an endocrine disruptor. And so we're now looking for safer alternatives on these flame retardants. And the hydroxides of aluminium and magnesium are two of the key compounds that are being looked at in that space. They work slightly differently, but because they're high purity, they don't adversely affect the strength characteristics of the plastics. So, these areas require the very high purity sorts of products. That high purity market is only about 1 million tonnes a year. I talked about 10 million tonnes a year of magnesium oxide from mining. This is a much smaller market, but it will grow, and especially as those fire retardants move from bromine-based to magnesium-based, and as this demand for glass and more smart glass applications are developed, that will only increase. And our world-class 300 program with Korea Chemical is actually focusing on developing these markets for these new materials. I talked a little bit about the environment. We do have some benefits from the traditional processes. Our base process uses emits about 11% less CO2 than conventional processes. If we introduce recycling of CO2 from our roasting, it'll be about 46% lower than comparable processes. And that sort of work has been done by the German Aerospace Centre. We're also working with a variety of other stakeholders. We've talked about Sahara Forest and Yarra Fertilisers and the city of Karratha around the Pilbara. We're also working with the companies that can supply brine, so the salt operating guys and the potash operating guys. And that's critical for us to secure the resource that's going to go into this process for the long term. These sort of high purity chemicals are definitely going to be a material that's here for the future, and we envisage our process having a long 20+ year life. This is our pilot plant in these couple of pictures. So we're building a mobile containerised version, which is in the top left there, and that's coming out to Australia later this year to demonstrate in the real environmental conditions how things work. Once we do secure land and access to a brine source, we'll kick off on our feasibility study and get project funding. Our goal is to produce a plant, or to build a plant that's going to produce about 80,000 tonnes a year of magnesium carbonate or 36,000 tonnes of magnesium oxide. We're calling it a commercial demonstration plant. It's commercially viable and it stacks up at that. It probably isn't big enough to adversely affect the markets that we're entering into, but it only uses a very small proportion of the magnesium in those brine streams that are available up in the Pilbara region. We'll create local jobs during construction and probably 25 full-time jobs during operation. As we continue to develop these markets through our world-class 300 program with Korea Chemical, we'll enhance these markets and continue to use these materials that have been used for years in new ways and in new applications. And really, we at EcoMag, we're looking for a long-term future with the new Pilbara. Thank you.